I will describe my project that uses the curryhoward correspondence for practical applications in generating code at compile time in Scala. But first, a short introduction into the curryhoward correspondence. This is a correspondence between types in the programming language, such as integer, string, or Boolean, and logical propositions. And also, this is a correspondence between code in a programming language and proofs of logical propositions. And the whole point of this project is to make some practical use of this correspondence. If logical propositions have proofs, it means that our programs can have code of a certain type, and we will see that if we can generate a proof of a proposition, it would mean that we can generate the code of the corresponding program. To see how this works, consider code that looks like this in Scala. This code shows that at some point in our expression, in our program, we can compute a value of type t. So let's consider this as a proposition and denote this by ch of t, meaning that code has a value of type t at some point. So that is the correspondence. So for each type, we have a proposition. Now, this proposition could be true or false for any given type, depending on whether the program is able to compute a value of this type or not. So for each program, this could be a different true or false proposition. Now here in this table I summarized different kinds of types that one can build in Scala. For example, here's a simple type variable. This is a tuple of two values a and b. This is a either of a, b. This is a type that has one of these two values. This is a function from a to b, a unit type, and a nothing type. Let's see what kind of propositions correspond to these types. Consider this, for instance. So this is a tuple of a and b. If we are able to compute a value of type tuple ab, it means certainly we have computed a value of type a, and also we have computed a value of type b. So on the logical side, it means we have ch of a, and also we have ch of b. So in the logical notation, this would be a conjunction of propositions a and b. Now in the short notation, I will just write a instead of ch of a for brevity. So this would be conjunction. The either type means that if we computed a value, let's say x, of this type, it means that we computed maybe a or maybe b, but we don't know which one. So we have computed one of these two for sure, but we don't know which. So that, in the logical side, corresponds to having a proposition ch of a, code has an a, or code has an b, but not necessarily both. So that is the disjunction, logical disjunction. So if we have a function type like this, it takes an argument of type a and returns a value of type b. Now, the logical side, it doesn't really mean we have a value of type a, it also doesn't mean we have a value of type b. But if somebody gives us a value of type a, then we can apply this function and get a value of type b. So in the logical language, if we are able to compute a value of type a, so if ch of a, then ch of b. So that's a logical implication from a to b. The unit type is always present, is always available to compute. So this is the proposition that is identically true. For every program, this proposition is true. And the nothing type corresponds to a proposition that is identically false. For every program, it is not able to compute any values of type nothing. So this is the correspondence between logical formulas and type expressions here written in the Scala syntax. Also note that type parameters, such as in a function that is parameterized by type, means on the logical side for all t. So it's a universal quantifier. It means for every proposition t, then something is valid. Here's an example. This is a Scala function that takes a value of some type A and returns a tuple of A and A of the same type A. So because this function works for every type A, the logical formula that corresponds to this type is that for every A, it follows from A that A and A. This symbol I should have replaced with this symbol. I will fix that in the slides. This is the conjunction, the logical end. So another important side of the curryhoward correspondence is that some propositions are valid theorems, that are they're true. Here are some examples of valid theorems, and corresponding to them there are function types that can be implemented in code. So for example, this proposition means that for every type A, if we can compute the value of type A, then we can compute the value of type A. Well, that's not a very interesting proposition, perhaps, but that is just a very first simple example. So this certainly is a true proposition. It's a theorem. It is true that for every A, it follows from A that A. Now, the type of this in Scala could be written like this. It's a function that takes a value of type A and also returns a value of type A. And obviously, it just returns the value it was given. So this type corresponds to, this logical formula corresponds to the type of this function. And similarly for all others, for example, here we produce a true proposition, and here we just produce the unit value, ignoring this x. Here we take A and produce a disjunction of either A or B. Similarly here, we take an x of type A and produce a left of either, left part of either. So similarly here for the tuple, we take the left part of the tuple. And for this slightly more complicated example is a constant function that takes x and of type A and returns a function from B to A. And that's the function that ignores the argument B. And returns that x that was given. So valid theorems can be implemented, and non-theorems cannot be implemented in code, cannot be implemented at all. Here are some examples of non-theorems, or formulas that are not valid, not true. For example, from 1 follows A for any A. And the function of this type would be that it takes a unit argument and returns a value of type A for any given type A. It's impossible to do that. In Scala, you could cheat and return null, and that would crash later. So that kind of cheating is not allowed in this consideration. Another example of non-valid formulas, non-theorems, are that for every A and B, if you have A or B, then you get an A. That cannot be done. Here, this is in Scala would be an either of A and B. You cannot return A from an either of A and B, because what if it didn't contain any A? It would only contain B. You cannot produce an A then, and so on. So all these examples are of this sort, that you cannot produce a value because you're not given it. So here, for example, you have a function from a to b to a. So you're given a function from a to b, and you're supposed to produce a, but you don't have any a's. You have a function that consumes an a, but that's not enough. So none of these types can be implemented. So then there's a natural question to be asked. Given a certain type, can we implement it in code? Here's an example. It's not clear at all. This is complicated. Can you write a Scala function that returns this? Fortunately, the logic that corresponds to these formulas, and this logic is called constructive or intuitionistic propositional logic, has a decision algorithm. So there's an algorithm that takes any kind of expression of this sort or of this sort, any expression that's made of implications, conjunctions, and disjunction, and type variables, and decides if you can implement this, if this is a true theorem, that for all values of the type variables, some formula is true. So there's a decision algorithm. There are many such algorithms for this logic, and the library that I'm implementing uses one of these algorithms to perform the derivation of the proof. So it automatically finds proofs of these formulas or finds that they have no proof. So this theorem prover is implemented as a Scala library with macros. But before we look at that, let us look at some examples of how we would do this by hand, how we would derive functions from types just by hand. So here is an example. If you're not familiar with the reader monad, don't worry about this. But the reader monad is basically this type, and this map function treats a as a type parameter and e as a fixed parameter. So then you map a to b, and from e to a you get e to b. So how would you implement this? So let me just try to say, so I have type parameters e, a, b, and I want this type. So what should I do? Well, obviously, I'm supposed to have a function that takes at least two arguments. So let me call these arguments EA and AB. Now, I'm supposed to produce a function from E to B. So that would be E going to something of type B. So how can I get something of type B? Well, I don't have any values of type B anywhere. So this is not of type B. This is of type E to A. This is of type A to B. So the only way I can get a B is if I apply this function AB, which is of type A to B, to something that has a type A. So I need to apply A to B to something of type A. Now, how do I get something of type A? The only way is if I apply this function to something of type E. So this function is EA. Now I need to apply EA to something of type E. And I actually have something of type E right here. So I'm done. I have implemented this function. And in fact, if you trace the reasoning that I just performed, there's no other way of implementing this function. There's no other way of getting a value of b except by applying this function of type A to B to something of type A. So and the same was on the next step. So all of these steps were forced on me. I had no choice. So that's an interesting observation, in fact, that there's only one way of implementing this function. Of course, it's important that I'm writing pure function. I'm not writing any side effects. So I could say, for example, something like this. That's possible in Scala. Would not be possible in Haskell, for example, because it's much more stricter types. It would prohibit you from making a side effect in the middle of a function. But in Scala it's possible, so let's not do this because this is not particularly useful. The useful and non-trivial part is this code. And that code is completely specified by its type. So there is no choice, no freedom. Once this type is given, there's only one expression I can write. The next example is to show that one cannot implement this function. So let me try to do that. So how would I do that? Well, I'll reason the same way. So let me remove these parentheses because they are not necessary to make it clear that I have actually three arguments here. So EA going to EF going to F going to and then something of type A. Now, how do I get something of type A? The only way to get it is to apply this EA to something of type E. So I could write EA of something of type E. Now, how do I get something of type E? Oops, I can't. There's nothing that returns an E. I'm not given an E. There's nothing I can do. So, in fact, I cannot implement this function because there's no way to produce a value of this type E. I have no idea what type that is. I'm supposed to produce it for any type, and I can't. I have no data to do that. Final example is to implement this function. So this function has two type parameters. Now, let's see. Obviously, I have to match on this option. There's no other way. Now, I need to produce an option of B, so I should be getting some B's at least, and the only way to get it is to apply this A to B to something of type A. So let's see if I have something of type A. I need to match on this option. So let me say is option A match. Actually, let me write this like this so that it is a little more clear. So this is option A, this is AB, and now I'm supposed to produce something of type option B. So what are my choices in doing this? I have two choices. I have some value. Now this value is of which type? Is of type A. Now if I have a type A, that's what I wanted. I can apply this function AB to this value. I can get something of type B, and now I can return some of this. And if I have none here, then there's no way for me to produce a value of type A or of type B. So the only thing I can return is none. Now this is one solution, but actually another solution would be to ignore that and to just return none in both cases. So I could ignore this value even if I have it and I still get the right type. I still get the type option B. But that would be uninteresting. That would be ignoring everything I'm given. I'm given this, I'm given this, I ignore all of that and always return none. So that's a very useless function, which probably is not what people want to use. And this is a much more interesting function, the map on the option, implemented in this way. So that was my reasoning. And this is how we can implement these functions. Note that in all these examples, we had essentially one way of implementing the function. With this example, we had a second way, but that was really not interesting and not useful. In this example, we only had one way. So why not have the computer write these functions for me, if there's only one way of writing them? Surely there must be an algorithm of producing that single implementation that is possible. So that is what the curryhoward library is doing. There are two main use cases. One is to define new methods. So suppose you define a method. A method is just a Scala function that has this syntax, and it can have type parameters. So imagine I wanted to implement that map function from the previous slide. So it has two arguments, e to a and a to b, and it produces e to b. In the more conventional Scala syntax, I would write it like this. I would put the arguments on the left-hand side like this, and then the type of the function return value, of the function's return value, is e to b. And then I just say implement. Implement is the function from the curryhoward library. And that's it. That's all I have to do. This is a macro. It will read the types on the left-hand side. It will perform the reasoning that we performed in the previous slide, and it will generate the code. Pretty much the same code. There's not much else it could generate. The second use case of the curryhoward library is to use the function called ofType. Now this function needs to be provided with specific return type, and it can also get arguments of specific values of some arbitrary types. It performs the same thing. So imagine we have some computation here, and we can build the expression out of parts in only one way, essentially. Here's an example, a little contrived example, but a simple one. So suppose we have a function of this type, and we have a case class that has integer and string parts. And we get some string and we get some boolean. So because we have a string, we could so now we are required to produce a value of this type. We're required to do that. How can we do that? Well, we have a string, so we could put the string in here, in this part. But here we have an int. So how can we get an int out of string, out of a boolean constant true, and out of this f? Well, we can put the string and the boolean here into f as arguments, apply f to abc and to true, and then we get an int, and this int we can put into the result. And then we have everything we need. So again, there's only one way of doing this without getting into the details of these types. So if all these types were type parameters, like a, b, and c, then that code would be the only solution. So the curryhoward library treats constant types as if they're also type parameters. It will never generate some non-trivial functions for integers or strings. Only we'll take the values and put them somewhere without change. So these are the two main use cases: to define new methods and to construct expressions from previously computed parts. The syntax is a little different for technical reasons. The library right now is in development. It is published on Maven. It has a website on GitHub, which is this one. I have some documentation here and the tutorial, which I encourage you to look at. The features that are implemented right now are that the types you can use are arbitrary combinations of function types, of constant types like int, string, and so on, that are also treated as type parameters. You can have any number of type parameters you want. You can have tuples, sealed traits with case classes or case objects. Another feature that I will talk about a little later is that sometimes there are several implementations of the same type available, and the library uses heuristics to try to choose one of them. And if this choice is possible on some grounds, then this will be returned, otherwise it will be an error. So there is some heuristic intelligence choice, so to speak, of the solution. Similarly to what we did with this code when we decided that this implementation is useful while the implementation that returns none all the time is not useful. So this is a heuristic that the curryhoward library implements. Here are some examples of how we would do the same thing using the curryhoward library. So basically you would just do this. The implement requires an import and you're done. This function is done. It is implemented. You can use it. The code is basically this, and this code has been generated at compile time and already compiled. So there is no runtime penalty for this. Let's see if we can implement that one. So let's run this test actually to see how this works. Right, so you see some diagnostics here. You see this first message tells you what was returned for this function. It's basically the same code. B, instead of these names, it uses simple names like A, B, and C, but it's the same code. Just the notation is a little more terse. It is a lambda calculus notation, but it's obviously the same code. Now there's an error here. This cannot be implemented. This tells you even which code was returned for the other function. This is a Scala code, actually. So you see the Scala code is exactly what you would write by hand. Going from A to C to A of B of C. So that's good. And finally, we can implement the option. Oh, I didn't do the option. Let me do the option. Done. Let's see what this option actually does. So let's say x is some integer option. So x is of type option int. Let's say, and let's say we have a function f of type int going to string. Let's say, just for an example, something like that. So now we want to use this function on this data. Map of x of f. And that should equal sum of 1 to 3 ABC, as if we are correct in what we are doing. We need to comment out this. You see, this is a compile time error. We cannot implement this type, and it's a compile time error. I cannot proceed unless I comment it out, or I make it into a test that expects a compile time error like this. So let me run this code again. All right. Tests pass. So you see, the library automatically chose the implementation that seems to be the most sensible and reasonable for this function. And let me give you some other examples of what you can do. For example, the distributive law, which would be translated into Scala code like this, is an isomorphism between, or equivalence of types between the either of A, B, and C in a tuple, and an either of tuple AC, tuple BC. So if I wanted to implement this, I would do something like this. So I'll put one arrow into one direction, and I'll make another one in the opposite direction. So just one syntactic detail that in Scala, tuple type needs double parentheses when it is argument of a function. So let's see if this compiles, because if it compiles, then it works. There's no runtime check. It's a compile time check. Yep. And so more complicated functions are available in my repository in the test code. For example, I have a test file that checks some functor laws and other laws. So here is, for example, the implementation of point, map, and flatMap for reader monad. So the types we already seen. Here's flatMap. And then I have some helper functions that check the laws for some specific types, chosen more or less arbitrarily. So these check the laws for code that was generated automatically using this macro. And here is what you get for the state monad. The function. So state monad is a type which is like this, where S is a fixed type and A is a type parameter. And so the point is a function from A to this, and you have a map which is a function from this, then AB, and then that, and so on. So this is a standard monad, which is called the state monad, and these are the standard functions, and the library can implement them all correctly. Now there's one thing when you actually run this, you will get warnings because there are several possible implementations of these functions. However, there are heuristics that allow you to choose one of them. So, for example, in the state monad, this function has two different implementations because it's supposed to return a value of s, and there are two possibilities. You can return the value you were given, which is right here, or you can return the value that you took through this processing function. So the state monad makes updates on state. And so you can have initial state, you can update it, and you have a new state, and you return that. That is the desired way to implement the map function. If you don't do this, if you just take the old state and don't update it, it means you're ignoring some of the data you're given. You have computed this tuple, but then you have ignored part of its value. So there's an algorithm in the curryhoward library that counts how many values have been ignored, how many parts of some tuple were ignored, how many arguments of functions were ignored. And each implementation has a score according to how many things it ignores. And then the algorithm finds the implementations with the lowest score. That is, the implementations that are the least lossy in terms of information loss. And that seems to be a good heuristic. Of course, you have to check the laws, and the library will tell you what it returns. So let me now talk about how this library works under the hood. So I will not talk about Scala macros so much. I can just very briefly explain how they work. So it examines the context of its enclosing symbol and detects all these types. It builds a syntax tree for the types, and then it runs the theorem prover, which I will describe momentarily, obtains the syntax tree of the code that should be generated and transforms that into the Scala code. The syntax tree is very limited. It only contains operations like applying functions to an argument, taking elements out of tuples, and making a match on a case class. So let me therefore concentrate on the theorem prover. That's the most interesting part. So logics have been studied for a very long time by mathematicians, and the logic that we are talking about is called the intuitionistic or constructive logic. And the first scientist or mathematician who studied this logic and got some algorithmic results was Gerhard Gentzen, who published in 1935 the rules that I'm going to explain here. My notation is again a little off. Instead of plus, you should read the disjunction, and instead of times, the conjunction. But I will fix that in the slides. So what does it mean, the calculus LJ that Gentzen discovered? This calculus is a set of axioms and derivation rules such that these will yield, if you apply axioms and derivation rules in any order, it will give you all the valid theorems of this logic and only the valid theorems. It will never derive anything that is incorrect, and also it will not fail to derive something that is correct. So he proved that for the constructive logic, these are the rules. So let me now explain how we can understand this notation. The basic element of this notation is called a sequent. This is, for example, a sequent. And this is another sequent. A sequent is a pair of left-hand side, which is the set of formulas, and the right-hand side, which is a formula. The left-hand side is called premises, the set of premises, and the right-hand side is called the goal. And sequent is a task of proof, is something we have to prove. So we need to, if we say we prove a sequent, it means we prove the goal of a sequent given the premises. How can we now read this notation? Now this notation is that there's a sequent on top, there's a sequent at the bottom, and here's the name of the rule. So this name doesn't really do anything, it's just a label. So you can ignore this for the purpose of understanding what the rule does. It's a label on the rule. So the rule consists of the numerator and denominator, and so to speak. So the upper part is what you might be able to prove first, and if you prove that, then you can prove this. So if you're able to prove this sequent, then you're able to prove that sequent. That's the rule. An axiom is a rule that has no required sequence to prove first. So here's an example. The identity axiom means that you start with no sequence you have proved, and you can prove from any number of premises that includes some x, which is atomic. Atomic meaning it's a variable, it's not an expression, right? So this is a type, in our context, this will be a type variable or a specific type. So if you have that among your premises, then you can derive that as your goal. The true rule, or T rule, is that whatever your premise is, you can always derive true. So this sequent can be derived from axiom, and this sequent, these kind of sequence can be derived from axiom. Now, if you have a sequent like this, and also you have a sequent like this, so both of them you have proved already somehow, then you can prove this sequent. That is the derivation rule called the left implication. Left implication meaning that the implication is on the left in the premises here. So I put this in blue in order to emphasize what is the interesting thing that this rule is transforming or changing. So for example, on the left of this table, there are all the left rules, and these rules deal with some interesting structure on the left. On the right side of this table, I put the right rules that deal with the kind of same structures, but on the right, in the goal. So let's follow once again what one of these rules says. So actually, to prove a sequent, what do? We cannot just start from these axioms and try to apply all kinds of rules randomly, waiting until the sequent comes up. That will be completely wasteful and we'll never finish. We need to start from the sequent we want to prove and imagine that this sequent is at the bottom of some rule. And then we find what other sequence we need to prove first in order to prove that one. So in this way we go bottom up and we make all possible applications of the rules if we find that the bottom of the rule matches the sequent we need to prove. So let me show you how this works on this example. So this is a sequent that has no premises. There's empty set of premises, and it needs to prove this formula as a goal. Now these are the typical sequence we will have to prove. So why is that? Well, look at this, for example. Well, this can be read as a sequent that has these two as premises, and this is the goal. This can be read as a sequent that has no premises, so arguments of a function are premises, and the return type of the function is the goal. So that's why being able to prove a sequent is analogous to being able to write code for a function of a certain type. So the premises that you have become your function arguments, and the goal becomes the type of the return value. So if we wanted to implement a function that has no arguments and returns this type, that would be the sequent. So let us follow through with the derivation of this sequence. It turns out that this is a theorem. It can be derived. So we start with a root. We make a search tree, so to speak. The root of the search tree is this initial sequent. Which rule can be applied to it? So the sequent has nothing in the premises, so none of these rules can apply. Only these. Now, which one of these? Well, obviously, only this one, our right implication, because we have a sequent that has an implication as a goal. So the implication has the first part and the second part. And the rule says, if you want to prove that, you first have to prove this. So you put A on the left-hand side and B stays on the right-hand side. So that gives us a sequent S1, which now looks like this. It has a premise, which was this one. It got to the left-hand side, and the goal stays here. So now we need to prove S1. So how do we prove S1? We try to see what rule applies to it. So what rule has this thing at the bottom? Well, obviously, it's a rule L, left implication. Now, the rule left implication applies when you have one of the premises of the form of the implication, right? This. So what I emphasized in blue, A to B, is actually this. So A is R to R and B is Q. So this rule says now we need to prove two sequences. One is this one, gamma A to B goes to A. So we just replace the go with A. And the second sequence is gamma B goes to C. So if we do this substitution, we get these two sequences, S2 and S3. So now we have to prove two sequences, each of them separately. So let's look at S3. It looks like a very simple sequence that immediately follows from the axiom identity. So that's good. We have proved it. Now it remains to prove this one. So we can again apply the rule L, left implication, because we have an implication on the left. Let's do that. Now if we do that, we get these two sequences, S4 and S5. Note that S4 is exactly the same as S2. And S5 is something else. Now we can prove S5, but that won't help because we are going back to having to prove S2. So we're in a loop. We wanted to prove S2, and rule left implication tells us we again have to prove the same sequence. So this is a no-go. We need to backtrack, so we erase S4 and S5, so we undo this step. So after this step, we need to apply some other rule to S2, not the left implication. Well, another rule that applies is the right implication, because S2 has an implication on the right. When you do that, you get the sequence S6. The sequence S6 has an R in the premises and an R as a goal, and so that follows from the identity axiom. So we have proved S0. Now, proving is nice, but actually code corresponds to this. So how do we get the code that corresponds to this proof? So we need to build something that's called a proof term. Term is a terminology in lambda calculus. Term is an expression. It's an expression that has functions and arguments and applications of functions and so on. So terms are actually code. So if we find that term, that means we have written code that has the type that we want. Now, proof of a sequence, if we had a sequence like this, then proof of the sequence is an expression which has this form. It's some kind of function of the arguments a, b, and c, such that the result of this function has type g. And the arguments of this function have types a, b, and c. So recall that sequence corresponds to function type. So on the left are the function arguments. On the right, so these are, or rather, types of the function arguments. So not actually the values. Sequence corresponds to types, not to values. We are now trying to go to and get to values. So we need to build expressions with values of type A, B, and C that altogether give you a type G. That expression is the proof term. This is how it's called. It's the proof term of this sequence. Now, each rule has a proof transformer function. Recall that each rule says, if you want to prove this, you have to prove first this, and also you have to prove this. Now, proofs are expressions, and so each rule also comes with a proof transformer function that says, what is the expression that proves this, given that we have an expression that proves this and another expression that proves this. So that transformer function is literally a function of these two arguments and gives you this as a result. So it takes the proof of this as the first argument, the proof of that as the second argument, and returns an expression which is a proof of that. So these are functions that we need to build. So let us trace again the same derivation of the same sequent, which was here. But now building the proof terms. So to build the proof terms, we have to start backwards from S6 back to S3, S2, S1, S0. Because that's the easiest way, because we start from axioms then. So that's actually, once we have proved a sequent, we know the path from the axioms back to this expression. And that is the path that we will use to build up the code, or the proof term, which is the same thing. So start with S6. So S6 is this sequent. It's proved by axiom, and the proof term is a function that takes these two as arguments, these two values of these types, and it needs to return a value of type R. Well, obviously this function is very simple. It takes, let me call this function T6 for the proof term, term for the sequence 6. This function is very simple. It takes R, RQ, and R, and just returns R, so it ignores this argument. The sequent S2 was obtained from sequent S6 using the rule right implication. So what is the term for this proof? Now this term is a function T2 with one argument, because the sequent S2 has one argument. How do we find this function? Well, this function is of type R to R, because that's what the sequence goal is. And we have T6, which is a function of this kind. So we apply the proof transformer for the rule right implication to the proof term T6. And the rule transformer takes that term and extracts R out of it and makes a function like that. Let me remind you that the rule right implication is like this. If I have this proof term, I should produce a proof term with a function as a goal. So that's how it works. So the proof transformer takes a function of this type and returns a function of that type. It's really only one way to do it. If you have a function from RRQ, R to R, and you need a function from R to R, then the only way to do it is this. S3 followed from axiom. So the proof term for S3 is just a function of Q that returns Q. The proof term for S1 is a result of proof transformer for the rule left implication applied to the two arguments T2 and T3. Remember that this rule has two sequences that it creates. And so if you want to prove this, you have to prove both of them. And we have proved both of them, that's T2 and T3. So now we apply the proof transformer for T2 and T3. And that's the proof transformer. It takes T2 and T3 and also this argument, and it just mixes them all together in the right way to get the right type. There's only one way to do it again. Finally, the term S0 is obtained as a proof transformer for the rule right implication applied to T1, which gives you this. So finally, you can simplify this entire expression by substituting all these functions into each other, and you get this expression. This is the term that the curryhoward library would derive. And this is how you can derive it using the Gensen calculus by hand. Now, each step here is trivial. You apply functions. All these functions pt are fixed. They can be written in advance as higher order functions, and you just blindly apply them. Once you know what the proof is, you just apply them and get your term. Now, one problem with the Gensen calculus is that it generates a loop. So we have just seen that when we tried to prove that statement, that sequent. As soon as the rule of left implication is applied more than twice, you get the same sequent back. And that's a loop, and you don't know what to do. Maybe you're doing something wrong, but it seems like you can apply this rule, so why not? So this complicates things. So these people, Vorobyov, Hudelmaya, and Dykhoff, they worked for a very long time on this, and finally they discovered how to fix this problem. And the result is called the calculus LJT. In this calculus, and again by calculus one means just a set of axioms and derivation rules, all the rules that we had here, except the problematic rule, the left implication, all the rules are kept, and the left implication is replaced by 4 different rules. And these 4 rules are basically doing a pattern match on this left premise A to B. This left premise could be an atom, or a primitive type implication going to be, or it could be a conjunction going to something, or it could be a disjunction going to something, or it could be an implication going to something. So there are no other possibilities in the logic. There are only these operations. So if that is true, then these 4 rules are sufficient. And they actually proved that this calculus is equivalent to the calculus LJ, except that there are no loops. So you can just apply these rules in any order, you will never get a loop. Which means that each rule will deconstruct your expression a little bit more, and you will get a search tree. You will never get a loop. It will be a finite search tree. You can just go through the entire tree exhaustively, and if you find no proof, then at some point you will finish your search and you will discover that there's no proof, so your sequent stays there. It doesn't have any more rules to apply, which means you cannot implement the type. There is no proof of that formula. Or you will find a proof, because this is a finite search, you can just go through it. Now these rules are kind of obvious, such as if you want to prove your premise has this, then it's the same as if your premise had that. Well, obviously these two are equivalent. Now the non-trivial rule is this last one. It exchanges the order of implications. So you have an implication from A to B going to C. To prove that, you prove implications from B to C. So you cross this parentheses. You get B to C and A to B. So that is a non-trivial thing. So why is this rule valid? Why is this rule? Why are you allowed to cross the parentheses? So this is based on a key theorem, which is the equivalence of these two expressions in logic. So these two logical formulas are equivalent. Each one follows from the other. This theorem is necessary to show that this is a valid derivation rule. So this is this theorem was the discovery of Vorobyov. In 1958 was published. Now, here is the quotation from the paper of Dikhoff, which gives you this expression. So this CDB goes to CD if and only if DB goes to CD. So there's this crossing. So you see D and B are separated by parentheses here, and then you have D to B without parentheses. So this is the same statement as I had on the previous slide, and the proof is trivial. So it wasn't trivial for me, but you know how mathematicians are. For them, everything is obvious and trivial. However, you can prove this, and a step towards proving this would be this much easier theorem, whose proof is really obvious. This is the proof term. So basically you take this f, you take a b, and you make a constant function that returns b always, substitute that function in here into f, and you get a c. So this is a kind of a stepping stone to proving that, because this is the way you cross the parentheses. You see, here you had b and c separated by parentheses, and here they're not separated. All right, so this is, I just wanted to say, so in the Curry-Howard library, I'm implementing this calculus, the LJT. I'm not using the LJ because I don't want to deal with the loop detection, and the calculus LJT is more efficient, and that's what's implemented. In my tests, I actually verify this identity. I can implement both sides automatically, and I can get the terms, but when I look at them, I don't understand anything. It's just a jumble of letters and terms like this in large number of different combinations. So to conclude, what can we do now having this technology? If we have a function that has a fully parametric type, that all types are type parameters, then we can decide whether the function can be implemented in code. And this is algorithmic, so the algorithm is implemented by the Curry-Howard library, and the library will also generate the code. It will fill in your code when it is trivial in the mathematical sense. It is obvious and trivial, and there is only one way of doing it, then it can be done automatically. So in the language of type theory, they say type is inhabited when there is an implementation of a function of that type. So whenever types are inhabited, they can be inhabited automatically. And what is something we cannot do with these tools? We cannot automatically generate code that satisfies some non-trivial properties, such as isomorphism or more complicated conditions, such as array must be sorted or number must not decrease or something like this. So in the Curry-Howard library, I implemented some heuristics to help generate code that has a higher chance of satisfying interesting properties. So I discard functions if I have several different implementations. I discard implementations that lose information in favor of implementations that don't, if that is a choice. And that is done in hopes of generating code that will satisfy more interesting properties. But I cannot guarantee that. Much more powerful type systems, such as dependent types, are necessary if you want to encode in the type that certain property, certain non-trivial property is satisfied, such as what we saw before in the option here. We might want the identity law, that this map function, when used on an identity function, does not lose any information from the option. It takes your option and returns the same value. So that would be a law that we would like to have, but it is impossible to express this law in the language of these types. Much more powerful type systems are necessary. And so the curryhoward library will not be able to do that. If you want to do that, then go and use those languages. But right now in Scala, we can do a lot and generate code for practical use. That concludes my talk, and here are the references that I used while implementing the library.